Okay, so we're finishing up the 6.3 consolidation activity, and then I'll get started on the homework. So you guys had to finish this for classwork, and remember, I'm taking a lot of classwork grades right now, so I do this. Okay, so the last part is we had to make up our own situation. So in class, we made up a situation of I'm at a concert, I paid $10 to get in, and each snack I buy costs $2. Well, we figured out that the variables were the two things that change constantly. And the two things that change are the number of snacks that I buy, so number of snacks bought, and the total money that I spend. Well, we talked about it and we decided that the independent variable is the person who's in charge. So the number of snacks determines or changes the total money I spent. So if I bought 0 snacks, I still had to get into the concert to pay $10. So $10. This is a little shaky today. Okay, so I spent $10. If I bought 1 snack times $2, that's $2, plus I had to add the 10 to get in, so that's 12. Sorry, let me put this under here, maybe it'll be more stable. There we go. Okay, so if we bought 2 snacks times $2, that's $4, plus my 10 is 14. So I had to spend $14. If I bought 3 snacks times $2, that's $6 for snacks, plus my $10 ticket, that's $16. $4 times 2 snacks, times $2, sorry, repeat that. 4 snacks times $2 a piece, plus the $10 for the ticket, will give me $18. 5 snacks, I was really hungry apparently, 5 hot dogs is a lot, times $2 a piece, plus the $10 ticket is $20. Can you guess what this one's going to be? Probably 22. Let's see if we're right. 6 times $2 is $12 for snacks. Then $10 to get in. 12 plus 10 is 22, so that's right. Okay, so independent variable goes down here, so let's label that number of snacks. So this is number of snacks. The dependent variable goes on the y, so that's number of dollars spent. So here's 0, here's 0. So when the number of snacks was, we have to do the thing. So number of snacks, 0, 1, 2, 3, 4, 5, 6. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on. Number of dollars spent. Well, if we go up by 10, it'd have to go 10, 20, 30. And so our whole graph would be between those two, so that's not right. Let's go ahead and make it by ones. So I know I have to go up by the same amount each time, so I can't go up by 10 and then do 11, 12. I've got to go up by the same amount each time. So if I go up by 1, 2, 3, 4, 5, 6, 7, 8, ooh, am I going to fit? 10, 11, 12, 13, 14, 15, 16, 17, 18. Not going to fit. So let's go by 2s. Let's go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. That should get us there. So at 0 snacks, which is this line right here, so above the 0 snacks, I need to be at $10, so right there. Then for 1 snack, I paid a total of $12. 2 snacks, I paid a total of $14. So 2 snacks, follow that up to 14, so right there. 3 snacks is 16. 4 snacks is 18. 5 snacks is 20. 6 is 22. Remember, if I'm going too fast, you can always pause this and catch up with me. Now, should I connect this? Remember, if I connect this, I'm allowed to have a half of one of these. So can I have a half a snack? Can I walk up to somebody and say, you know what, I just want to buy half a hot dog? No. So you can't connect this, and it's called discrete data, because you can't connect it. You can't have half. Now the rule, look at this, we already did it. So the rule here is y equals whatever your input is times 2 plus 10. Well, my input is always x, and this x times 2 we rewrite as 2x. So it becomes y equals 2x plus 10. So my rule is always y, the dollars I spend, is the number of snacks I buy, x, times 2 plus 10. All right, that wraps up the consolidation activity. So let's go ahead and start your homework. Let's put your name on it just in case. All right, and let's see what we've got. Consider the following situation. A high school assistant principal is making the school's lunch period schedule. As shown in the diagram, the school has only one size. Wow, they are loud. Can you hear the band? They're walking by. As shown in the diagram, the school only has one size table for the lunchroom, and each table can seat 8 students. So if one table, you've got 1, 2, 3, 4, 5, 6, 7, 8. Okay. The assistant principal has decided that he will not push any tables together. When more tables are placed in the room, more students can be seated and fewer lunch periods are needed. The variables in this situation are shown. So number of people to be seated and number of tables. Where number of tables is in charge of how many people can sit. So number of tables is independent. That's in charge of or tells how many people can be seated. So this is my dependent. So which variable is dependent, which is independent? Number of tables is independent because it can change the total number of people that can sit. So we decided our independent variable is the number of tables. So number of tables, which is also x. Our dependent variable is who follows along. So the number of tables tells who what to do. Well, this is number of people that can sit. So that's y. So let's think about it. If there's one table, it shows that I can sit 1, 2, 3, 4, 5, 6, 7, 8. Now, if there's 2 tables, remember it said they will not push together. So if I add a whole nother table, I've got the 8 here, then 9, 10, 11, 12, 13, 14, 15, 16. Because they do not push them together, you're not missing or you're not losing that seat in the middle. So they're separate now. So that's 16. If I do 3, each table can seat 8. So 8 times 3 is 24. If I sit 4, each table sits 8 people. So 4 times 8 gives you 32. 5 tables times 8 apiece is 40. 6 times 8 apiece is 48. 7 times 8 people per table is 56. 8 times 8 is 64. And 9 tables times 8 people per table is 72. So we've got that. So let's see, our independent variable is the number of tables. And the dependent variable is the number of people. So number of tables basically goes up by 1, so we're going to do the same. Here's 0, here's 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now this I can go up by, I've got to get to 72. So maybe 5, 10, let's see if 5s will work. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. I think I'm going to fit 55, 60, 65, 70, 75, 80. Perfect. All right, so let's go ahead and plot these. At one table fits 8 people, so 5 6, 7, 8 would be right below the 10. 2 tables sits 16. So 2, here's 16 right about here. Here's 2 right there. 3 tables sits 24. So 24 would be right under the 25. So 3 and 24 is right about there. 4 is about 32. So here's 32, and here's where 4, so we're right about there. 5 and 40, so 5 follows the 40. 6 and 48, so find your 48 right below the 50. Come over to 6, and you get it right there. So 7 matches up with 56. So find your 56 and draw over. Bring your 7 up. And so it looks like this. Should I connect them? Can I have a half a table? No, do not connect. It is discrete because you cannot have a half a table. So let's finish answering the questions. All right, define the variables and write a function rule to describe the relationship between the number of people to be seated and the number of tables. Well, we said x equals the number of tables. I don't know why this is shaking so bad today, I'm sorry. Y is the number of people who can sit. So y is equal to, or the number of people that can sit down is equal to the number of tables that I have times 8. Simple on that one. Explain why your function rule makes sense in the context of the problem. Because you can sit 8 people at each table. So, to find y, you just multiply the number of tables by 8. So use your function rule. So immediately when you see use your function rule, start with your rule. How many tables? Is my tables my x or my y? It was my x. So how many tables means I'm looking for x. For 500 students, y was the number of people, so 500. So what number needs to go in here? 8 times what equals 500? So you need 40 tables. You can check and guess that. Guess and check. All right, I've already pretty long, so we're going to go ahead and make 2 videos today.